This is a video to show how to do a two-proportion hypotheses test, or z-test, and a two-proportion confidence interval after the hypotheses test. So we're going to use the class example where Mr. Hardy had a small bucket of beans, red and white beans, and a large bucket of red and white beans. And the idea, if you read the problem, is basically students want to prove that the small bucket has a larger proportion of red beans. Okay, and they want to use an alpha value, a significance level of 0.05 for the test. So first, let me point out some notation. So if we did a census of this bucket, we could clearly answer the question. And we would use this notation, P subscript S, to be the proportion of red beans in the population of beans in the small bucket. And we would use P of L to be the population of red beans in the large bucket. Now, if it was a real serious issue, we really had to know, we could count every bean in both buckets and determine these. But that's a hassle, so what we'd rather do is just take a small sample from each, large enough but small enough sample from each. So we did that, but before we do that, let's look at our hypotheses. Our null hypotheses would be that they're the same. So the percentage of red beans in Mr. Hardy's small bucket is the same as in the large bucket. So the difference in the two proportions is equal to 0. So the only way that could be is if they're the same. So what we're saying is P subscript S equals P subscript L. Okay? And then what we want to prove is always in the alternative. So the percentage of red beans in Mr. Hardy's small bucket is greater than the percentage in the large bucket. So here we say P minus P of S minus P of L is greater than 0. So those are our hypotheses. Now, in 7th block, we took a sample, and here are the numbers we got. We took a sample in class, and we had 676 in the total sample, with 309 red beans. So our sample statistic was 309 divided by 676, and so that turned out to be 0.457. So this is actually our sample statistic, our observed value for the sample in the small bucket. Now in the large bucket, we ended up taking 1,090 beans, and of them 375 were red. So we have 375 divided by 1090, and that gave 0.344. So already we can see a pretty big difference. But the point behind a hypotheses test is we have to rule out that this difference is due to variability, because it could have been. So we have some preliminary data established, and we have our hypotheses established. Now, so what we want to do is use a model, and we already know the hypothesized value of this model is 0, because what we're going to do is we're modeling the difference. Okay, the difference in the two proportions. So before we can use the model, we got to check the conditions. So let's see, from the size of the two buckets, the sample sizes of 676 and 1090 appear to be less than 10%. So we're good there. We assume that the sources of beans in the small bucket are and I should say, let's say we assume that the sources of beans in the small bucket are different. How about in the buckets are different? That makes a little more sense. Success failure condition. Well, now we just have 4 of these. So to do. So 676 times p hat, the sample. So here's the beginning of something new. So I'm going to try to point these out as we go along. So usually, up till now, we've had actual hypothesized values, but we're not really hypothesizing what the percentages are. We're just saying the percentages are the same, or the percentages are different, depending on the statement. We're really not speculating, so we really don't know. So all we can do is use p hat to do this check. Okay, so that's something new that you got to watch for. So let's see, this is going to be 1 minus 0.457. So that's going to be 0.543. And then over here, this is 1090, 1090, and this was 0.344. And let's see, this one was 0.656. So 1 minus 0.344. Okay, so the results shouldn't be too surprising because our sample sizes are so large that we're going to be able to meet this condition pretty easily. But you do have to do this, and if you don't, you're really not on solid ground to use a normal model. Okay, so we've done the computations. So all are greater than or equal to 10. So both sample sizes are large enough. Okay, so the only thing that's different, I apologize, a little clumsy here. What's different now is that we need the samples to be independent of one another. So, you know, the color of one bean does not affect the color of another. That's what we've been doing up to now. But we also have to say that the groups are different. And you have to sort of just trust Mr. Hardy that he acquired the beans from different sources for the 2 buckets. Okay, so now the conditions for inference are satisfied, so we will proceed with a normal model of the sampling distribution of the difference. And you could say difference in proportions. And perform a one-tail 2-proportion z-test with an alpha level of 0.05. Okay? So now the conditions are met, so now we can proceed. So the model has a mean of mu equal to, and then we have to use some notation here because what we're saying is PS minus PL, but what this is the differences in samples, sample proportions. So this is what we are expecting. So we have to put hats on these because we're really building a model of what we expect if we sample over and over again and get lots of differences. Okay, and then that center is 0. That's an extension of the null hypotheses, that this is 0. Okay, so now we'll use pooling. So here's a new concept, and we just do it for hypotheses testing for two-proportion tests. It's the only place we do it. But the idea is to take this hypotheses and just run with it until it leads us into a contradiction. So the theory is if this is true, if we're hypothesizing from the null hypotheses that the proportion in the small bucket of red beans is equal to the proportion in the large bucket, then essentially what we're really saying is this is just one big giant bucket. Okay, it's just one big giant bucket. I'm not sure I like that, but that's the idea, is that it's like taking all of these beans and pouring them into there, because there's no difference. And so all we did, it's like when I scooped up a bunch of beans here and scooped up a bunch of beans here, it was kind of like I just did a scoop and then another scoop from the same bucket, because what we're saying is the proportions are the same, so it doesn't matter. Okay, so when we do that, we're just saying we just take all the red beans. Okay, so what this is going to be is 309, because that was the number of red beans in the small bucket, plus 375 divided by the two sample sizes. I think that was 676 plus 109. Okay, so we're just combining those. That's what pooling means. And so far we're not comparing yet the sample statistic to the hypothesized or the theoretical numbers. So we get 387 when we pull it together. Okay, so this is going to be the basis for calculating our standard deviation, because that's what we need to finish the model. We have the center. So once again, because we don't have hypothesized values, we have to use the estimated values. So what we're going to do is use a standard error, not a standard deviation. And so it's like when we add two random variables, we have to add the variances. And so when you do that, you get this formula. So p hat pooled is going to be 0.387 times 1 minus 0.387 is 0.613. Okay? And we're going to divide that by 676. Then we have another term, but we use the same numbers, 387 times 0.615 divided by 1090. Okay, so you can actually do this in your calculator in just one entrance. What you do is you just say square root and don't put the parentheses in. Just say 0.387 times 0.615 divided by 676, and then just say plus, because the TI 83 and 84 it knows about order of operations. So just say plus 0.387 times 0.615 divided by 1090. You can put close parentheses and then hit enter, and what you're going to get is 0.024. Okay? So that is our standard deviation for our model. Okay, so now we have 0, and so this would be at this point right here, this is 0.024, so this would be 0.048, and so on. Okay, so now what we want to do, now this is where the rubber meets the road, is now we're going to compare the observed difference. So we have two observed values that we have right here, these two values. So what we want to do is we want to find their difference. Okay, so 0.457 minus 344, and we get 0.113. So this is our actual, like in before we just called it p hat, but now this is the difference in the two p hats. Okay, and we're going to compare that to the model. So the question is, where is it over here on the model? Okay, so probably the easiest way is to calculate the z value, because that's a measure of how many standard deviations away it is from the center. So don't let this notation, you don't have to write all this, but I wanted to make sure you knew that what these things mean. Okay, what this notation means. So the observed value is just this difference. It's the observed difference, so 113, minus the hypothesized difference. So this is actually becomes easy. It's 0. We're saying that the difference should be 0. And then we just calculated the standard error, 0.024. Okay, so all we're doing is we're just taking these two numbers and dividing 0.113 by 0.024. That's all we're doing. But if you look at the notation, it could be easily sort of intimidating. So the answer becomes 4.7. So let's see, 1, 2, 3, 4, 5. So it looks like it's right at 0.113 is right there. So we want to know what the probability is, what the area is from here out to infinity under the curve. Okay, so to do that, all we're saying, as I put it all together so that you understand it, the observed value, we want to know what's the probability that the observed value is greater than 0.113. So the observed value is just this difference using notation. Okay, and so that's equivalent to z being greater than 0.47. So we have 0.47 out to infinity, or 999, and that's going to be 1.3 times 10 to the minus 6. Okay, so essentially 0. So first, what does the p-value mean? Okay, so if there really is no difference in the proportion of red beans in the small bucket and large buckets, the difference observed of 0.113 will happen 1.3 times 10 to the minus 6% of the time due to natural sampling variability alone. Okay, so basically the model says it should never happen, but it did happen. Okay, so that's a contradiction. So we can say, hey, this model is wrong, but where did this model come from? Well, it came from the null hypotheses. So the null hypotheses must be wrong, because assuming it and following a logical series of steps leads to a contradiction. So now that we've rejected it, we can accept the alternative. So that's what we're doing here. Since the p-value of 1.3 times 10 to the minus 6 is small, less than the alpha value of 0.05, we reject the null hypotheses. There is sufficient evidence that the proportion of red beans in the small bucket is larger than the proportion of red beans in the large bucket. Okay? So that's our conclusion. Now you don't have to interpret the p-value unless they ask you. A lot of times on a test, it will come after you draw your conclusion. The key thing here is to make sure you say, am I rejecting or not, and why, and then add some contextual information. Now, the last part is oftentimes you need to say the conditions for a confidence interval have been satisfied. Something like that. So we can continue with, just say something like, with a confidence interval to estimate the difference in the proportion of red beans in the small bucket and the large bucket. We will compute a 2 proportion z interval at the 95% confidence level. Okay, so now we don't pool. We have no basis to pool for a confidence interval. So what we're going to have to do is we're going to have to calculate a regular standard error. So these numbers I remember, 1090, and let's see, the proportion of red beans in the small bucket was 0.457 and 0.543, I believe, and 0.344 and 0.656. So it's you just got to compare the difference between these. Here we're using the pooled value, so they're repeated in both terms, whereas here you're using the actual. So once again, you can calculate this with one command, and what you get is, because our n is so large, we really don't get a difference, but a lot of times you do get a difference. Okay, so we get something like that. So it's essentially the same, but that's because our sample size is so large. Okay, so the margin of error for 95% confidence interval is, this I have memorized, is z star of 1.960 times 0.024, and that's going to be equal to 0.04704. So I'm going to say 0.047. Okay, so what we're going to do is we're going to estimate the difference. So it would be p hat s minus p hat l, and we're going to subtract off that. So that's 0.113 minus 0.047, and then once again p hat s minus p hat l. Okay, so that's the observed value. So 0.113 plus, I have a minus right here, it should be plus 0.047. So the results are 0.066 and 0.160. So we are 95% confident that the small bucket has between 6.6% and 16.0% more red beans than the large bucket. Okay, so this can, because notice that 0 is not in it. Okay, 0 is not in the confidence interval. So that confirms our hypotheses. 0 is out here on the number line, and 6.6 is here, and 16.0 is way out here. So there's our confidence interval right there. It doesn't contain 0, so it makes sense that we rejected the null hypotheses. Okay, so that's how you do this problem. It's a long procedure, but that's kind of what we're doing. Okay, good luck.